Hello, my name is Maxwell Milroy, and I'm a junior studying mechanical engineering at Arizona State University. As part of my honors contract for my structural mechanics course, I am tasked with creating a video to help explain how to use the projection approach to solve a 3D equilibrium statics problem. As you can see in the upper left-hand corner, there's the statics problem which we will be solving. And basically what we're going to be solving for is all the reaction forces at point C, which is located on the wall. So two common methods that can be used to solve this is the vector approach and the projection approach. So as I mentioned previously, we will be using the vector approach to solve this problem. So as I mentioned before, this is a 3D statics problem, and we're looking to find the reaction forces at point C. And if you look over to the free body diagram, you can see at point C, because it's connected to the wall, you're going to have a reaction force in the Y, X, and Z direction. And you're also going to have moment in the Y, moment in the Z, and then torque in the X. When we use this vector approach, we are going to break this down into three different planes. So basically, not the vector approach, the projection approach. So the vector approach takes this and solves it using 3D. So we have a 3D problem, obviously, right here. So it uses 3D to solve it. Whereas the projection approach takes this 3D problem and splits it into three different 2D problems. And our ultimate goal is to solve for the 6 variables: AX, AY, AZ, MY, MZ, and the torque around X. Okay, and now we're going to solve the problem. So as I mentioned, we're going to use the vector approach and break it into three planes. So the three planes we're going to use is the XY, the XZ, and the YZ plane. So this is going to be the three 2D problems we're going to use to solve for the 6 reaction forces that we're looking for. Okay, so we're going to start with drawing out the XY plane. Okay, so if you can imagine, I have the coordinate system on the problem. So if you just imagine it, you're looking only at that direction. The problem would look something like just a straight bar. Okay, so this is what we have. So looking from the XY plane, we are only going to be able to see the force acting in that direction. These are the reaction forces at C. Sorry about that. So this is C, and this point right here is B. Okay, so this is going to be your reaction force. So this is going to be in the X direction. So we're going to label that CX. Okay, but you're also going to have the reaction force in the Y. So like that, and we're going to call it CY. Okay. So so if we look this way, as you can see in the XY plane, we're going to also be able to see the 105 acting, and also we're going to be able to see the 25 newtons. And also, so pretty much on this plane, you're going to be able to see almost all of the forces. So then we're also going to be able to see the 80 and the 75. So 80, 75, 25, CX, CY, and this is 105. And lastly, if you look in this direction, we would not be able to see the torque in the x or the moment in the y. The only thing in this direction we could see is the moment in the z. So we're going to put that as mz. Okay, now we're going to solve the problems. Okay, so first you have summation of f of x. Let's see if I can change. Hold on. Okay, summation of f of x. So forces in the x have to equal 0 because this is a statics problem once again. So if you look, oh, the other thing, I'm going to write down the coordinate system right here. So that's going to be y, this is going to be x. Okay, so if we look in the positive x direction, we are going to have cx plus the 80. And then the other only force we have is the 75, which is going in the negative x direction. So if we solve for cx, which is the reaction force at c in the x direction, as you can see, we are going to get -5 newtons. Okay? So, next, sum of the forces in the y. Again, it has to be equal to 0 because this is a statics problem. So, if we look in the positive y direction, we have cy, and then the only other one we have is in the negative direction. So we have minus 105 and minus 25. So once again, solve for this. You can see that cy has to be 130 newtons. Okay, so that's 2 of them. We still have to find 4 more. So then we're going to use the moment about c. So mc. So if we look, we are going to have 2 forces, both the 105 and the 25, affecting this moment. And as you can see on the drawing, I'll put it down here too. This bar length is 2 meters. So this has to be 0. As you can see, the moment is pointing in the counterclockwise direction, so we assume that to be positive. So we have mz. And then if you look, imagine the bar being pushed down, it's going to go clockwise. So we are going to have minus, and they're both acting at the same point at 2 meters. So it's going to be 105 plus 25. Sorry, that's a 25. Let me get an eraser. Oh, that's not. Okay. So that's 25. And that quantity is also going to be times by 2 meters because that's the length of the bar. So solve for mz. We find mz is equal to 260 Newton meters. Okay, the next plane we are going to solve is the YZ plane. We just did the XY, so now we're moving on to the YZ. So same thing, look at the coordinate system on the problem. If you can imagine us only looking at the YZ plane, it would again just look like a bar. So I'll put, that's not the right one. Sorry about this. The plane. Okay, so same thing. If you look at it, it's just gonna look like a bar. Okay. So now, from the YZ plane, this over here is going to be your point A. This side over here, I'm going to put it up here, put it down here, is going to be B. So if we look at A, we are just going to have the force, the 25 Newton force. But we are going to have a lot at C. So what we're going to be able to see is, again, 105. The 105. You're also going to be able to see, so at point C, we're also going to be able to see the CY, which points in the positive Y direction. CY. Sorry if that looks like an X. Let me fix that real quick. Okay. Okay, that's CY. And we're also at point C, we're going to be able to see CZ, which is in the positive Z directions, which would be this way. And let me once again draw the coordinate system. So in this case, in the YZ plane, it's like this, where this is Z and this is Y. Okay, and last but not least, let me label this real quick. Last but not, okay, this is CZ. And last but not least, at point C, we are going to be able to see the torque around the X, which I will read as X. Okay, same thing as before. We are going to construct the equilibrium equations. So this time, sum of the forces in the y direction is equal to 0. So in the y direction, based on our coordinate system at the bottom, we are going to have positive cy minus 105 minus 25. And that, once again, if you solve, that will give you a cy value of 130. And this is good because it checks out, because as you saw in the first part, cy we got as 30 as well. Okay? So now we are going to move on to forces along the z equals 0. So we are going to have CZ, and nothing else, as you can see, is in any C direction. So that's going to be our answer for CZ. And lastly, we are going to do the moment about B, which is that point with all the forces on it. So the torque is once again moving in the counterclockwise direction, so we know it's positive x. And then if you look at since it's at point B, none of the forces around point B matter because the length would be 0. But our 25 makes a difference. So if you just imagine you hold point B still and rotate and put a force at that end of like 25, it's going to rotate counterclockwise. So you would have plus 25, and once again it's 2 meters length as seen in the problem. So solve for Tx, or the torque along the x direction, and you are going to get negative 50 Newton meters. And then last but not least, we will solve the xz plane. And last but not least, we will solve for the xz plane. So same thing, use the coordinate system. Imagine you're looking only at the z plane, the xz plane. So we're looking down on the figure. So we are going to see the bar looks like this. Right? Okay. So from the top view, that right there is going to be point C. And our other point, well, actually we can see them all in this figure. So point B is right there, and point A is right there. Okay, so now we're going to do the forces that we can see. So let's start with point C. So from the top, we were able to see Cx. We're also able to see Cz. And let me draw the coordinate system so this is x, and that's z, based on the coordinate system we have on the drawing. So since we're looking up, we can't see the reaction force acting in the y direction at point C. So at point C, we also can see the moment. So I will indicate that right here. And that's going to be the moment in the y direction. Okay, let's go to point B. So looking from up top, we're not going to be able to see the 105, but we will be able to see the 75. And then we'll go over to point A. In point A, you won't be able to see the 25 because it's in the y direction, but we will be able to see the 80. And that's all the forces in the xz plane. So we'll once again do the equilibrium equations. So to start, f of x equals 0. Statics problem. So if we look in the x direction based on the coordinate system at the bottom, we see c of x is in the positive direction, as well as the 80, and then the 75 is in the negative direction. Okay, so solve for Cx, we get negative 5 newtons. Oh, great. That's the same thing as the xy plane that we solved, so we know we're doing something right. So next, solve for the F forces in the z direction. once again 0. So look in the z direction. The only force pointing in the z direction is the reaction force at C. And nothing else. There's nothing else there. So once again, C of z equals 0. Oh, awesome. That's what we saw in the YZ plane. Okay, and lastly, we need to solve for the moment about C. So all the forces around C will not be counted. 75 is in line with point C, so that will not contribute to the moment. But we have the moment in the y direction, which once again counterclockwise, so we know it's positive. And if we look at the 80, if you can imagine, hold point C still and pull with a force of 80, so the bar is going to go counterclockwise. So as we said before, counterclockwise is positive. So it's going to be 80 times 2 meters again, based on the drawing. That's the length. 2 meters. So for my, we are going to get negative 160 Newton meters. And that is how you solve for all the reaction forces at point C using the projection approach.